I want to talk about some supersymmetric Lagrangians. In the previous times that we already discussed the superfield. There are two types of superfield. One is the color superfield, and the other one is vector superfield. And we can construct the supersymmetric Lagrangians from the both superfield. So before that, the construct of such a Lagrangians, we want to define this integration, especially the such a superfield is defined on the superspace, which is some variables with the Grossman number. So we choose to define the Grossman integral. So Grossman integrals can be defined as the status integrals is equal to the zeros, and the status such integrals equal to the 1. Then if we integrate the a plus b status, such as functions defined on the superspace, then only the highest order terms remains after the integration. That's the rules of the integration in the superspace using the Grossman integral. And if we define this more complicated this integrals module, this Kiosadas as some quadratic sum of the term index A and B with the antisymmetric matrix. Also, we can define that this Kiyosada bar. So it is consistent with this Zeta bar components, which is the mean that there are some corresponding to the right hand is the pi spinner, and we can define that these four Zeta as this scale Zeta, this scale Zeta bar. And there are some of the several side entities for the such as integral module. For example, if we integrate the quadratic terms of the Grossman variables over the scale Zeta, and that will be 0 data 1. Also for that Zeta bar quadratic terms over the scale Zeta bar. It can be proved given like that. First of all, if we insert the scale Zetas, such a definition, we know that such a quadratic terms is equal to the minus 2 zeta 1 zeta 2 because of the rolling and the rising index of the such a Grossman variable. And if we suggest there will be the sum of this minus 2 zeta 1 zeta 2 terms will still appear. And if we use the sort of the definitions of the zeta 1's integrals with the zeta 1's and the zeta 2's integrals with the zeta 2's, and the ones will be the results of the integration. So so we can define sort of such a delta function, which is we can interpret sort of such a quadratic terms of the Grossman variables, that is the delta functions of the Grossman integration. So we will write delta functions scale status equal to the quadratic terms, and if we integrate some functions with the delta functions, then it will be zero that the function values at the status equal to the 0. There are some other proof, but there are some problems with the image captures. It's the reverse. And now we can construct the supersymmetric Lagrangians. So we know that the actions can be defined as some integrals over the some four-dimensional space-time, but not only the space-time. So we should integrate over the four Grossman variables for the supersymmetric Lagrangian case, and then we will obtain the Lagrangian density without the some of the Grossman variables. So we use all integrated out to such Grossman variables data. And reminds that the mass dimension of the Zeta is minus the 1/2. And because of the Zetas integrals, the defines of the 1, so such integral module d Zetas that has the mass dimensions of the 1/2. There are very different behaviors in the real number, because in the real number, for example, the coordinates has a mass minus 1 dimensions, but the axis also has a minus 1 dimensions. There are very different behaviors in the status of this other. And because the actions I is no mass dimensions, and such as space times d for x that has a mass minus 4 dimension, and we know that the d square stardust has a mass of the ones and another d square stardust bar. So such a this stardust for power series has some master of the 2 dimension. So such a Lagrangian should have the master of the 2 dimension. So here's some of the dimension analysis in the math. And we know that such is the Karashi piece that has the mass dimension of the 1. So there are some color views, which is also mass dimension is 1, and the spin-off views is mass dimension is 3 over 2. There's some well-known the box in the standard model, and we know that the stardust has a mass minus 1/2, so it's consistent with the Karashi of his mass dimension. And also we already know that the supercharge has a mass of the 1/2. So it's consistent with the partial stardust that has a mass of the 1/2, and such as there with the sum appears term of the linear combination of the such as stardust partial ox and the stardust of the mass minus 1/2, and the partial ox is the mass minus 1. So it's consistent with this mass dimension of the supercharge. And now we can construct the sum of the polynomial of the such a Karashi fields, and we choose the satisfy such mass dimensions in analysis. We learned that the Lagrangian has a mass 2 dimension, and we can construct the one color superfield of the complex and the one color superfield. It has a mass 2 dimensions, so is allowed. But there are so one color superfield, then there will be some of the mass 1 dimension, and we can give that this delta function. Then such a delta functions will remove this scalar term, and because there's some quadratic terms, so it has some of the mass minus 1 dimension. So such a term should be the mass of the 2 dimensions to contain the Lagrangians. So such a coupling has the mass 2 dimension. So such a term is forbidden because coupling constants are the mass dimensions. So such a term is like the non-real reachability. So we will remove such a term. And in the second term, if we give the t color shape of v pi I and pi j, and the delta function, then from the t color shape of v, there are the mass 2 dimensions and the quadratic terms, the delta functions that has a minus 1 dimension. And such a coupling constants MIGIs can be interpreted as the mass coupling constants. And for the third terms, there will be the 3 color shape of this, and it has 3 color shape of this. And also there are some of the delta function. It will give sort of minus 1 dimension. The coupling constant is no mass dimension. That's a very similar behaviors in the some color of these some of the polynomials form. And such as color shape field contains one color field and one spin field that shape partners and one accelerator field. If we calculate the component fields such as the pi or pi daggers, and we can calculate the full term. There will be some of the kinetic terms for the scalar fields and spinor fields terms will appear. There is a very various terms in the standard model. Some of the Dirac equation forms in the 2 component spinor, and that's the kinetic terms for the scalar field. Will appears, and also there are some of the accelerator fields terms will appear, but it will be removed because there are new kinetic terms there, and it will be discussed in the supersymmetric Lagrangian in the next time. And also we can expand this sort of other terms in the such 2 color shape fields or 3 color shape fields and the component field. And there are some cross terms with this color fields and accelerator fields, and such accelerator fields can be removed by the equations of the motion. Like that, because there are no kinetic terms in the Lagrangian for the accelerated field terms. So in the Euler Lagrangian equation, such as terms will be the 0. So partials and partial opposites are equal to the 0, and there will be some under some specific component fields terms will be appears in Lagrangians. And if we also there are some upscale terms. So if we derivatives of the ups in the Lagrangian, so there are these up terms and the remaining is the specific fields remains. So we can have signs of the up. We can express the up in terms of the other component fields. So we can remove sort of the auxiliary fields in the Lagrangians and such remove the auxiliary field to give us the supersymmetric Viking effect in maybe discussing next time. And also we want to construct sort of the supersymmetric Lagrangian from the vector Superfield. And we know that there are some Superfield strings and it contains some field strings term, while terms in standard models, and the kinetic term for the gas boson and is constant with the mass dimension, and also there will be the sort of appear that the kinetic term for the gas bosons, because the gas boson has spins 1/2, so that are similar to form with the Dirac equations as with the. And because there are such a feminist terms as a mass dimension of 4, there will be this additional quadratic terms will be appears to the mass dimension of -1. So let's check about some of the mass dimension. So actions that has a mass dimension of 0 and the space-time mass dimension of -4, and such is Superfield functional mass dimension 3, and there are some d-square same mass dimensions 1. So there is a very constant mass dimensional analysis with the supersymmetric Lagrangian construct by the vector Superfields. And also there will be some of the detail superfield appears at auxiliary bezier, and we can remove the maybe the next time. So in general, so we can write the normalizable supersymmetric Lagrangians with the Chiral and the vector Superfield. There is just the kinetic term as the Chiral Superfields, and the mass terms for the Chiral Superfields, and some interaction terms, self-interactions with Chiral Superfields, and the kinetic terms of the vector Superfield. And there will be some of the terms that will appear as after and the terms. And I think that's enough for the story to construct the supersymmetric Lagrangians.